I'm Tyler. I'm a Ruby developer focusing mostly on the back end, but I also work with the full stack. I have a philosophy degree from the University of California, Santa Cruz, and here's my info if you're interested. I've been working on a project these past few weeks called Tracebin. In essence, it takes the concept of a bin, like request bin or JS bin, which were designed as temporary tools for web developers, and it applies it to application performance monitoring. So it's a mix between JS bin and Relic, or its relatives. To understand what I mean by that, it's best to show an example of how it works. You go to the site. This is the Tracebin website. You click the button to create a bin, and then you follow these instructions to install the agent on your web application. And when you deploy your app, our agent will collect performance statistics on this page. This is a screenshot of our service up and running with a Ruby app, a Rails app. Tracebin will show the most recent 24 hours of data, including traffic and response times, performance data for your endpoints. We also have traces for the general execution flow for any given endpoint. And we also measure background jobs and some general system health data. Today I want to talk about the technical issues and best practices I encountered while developing Tracebin. This is sort of a schematic diagram of the service as a whole. I'll talk about it in a little more detail later on. Tracebin comes in two parts. We have the agent in green, which is the extension that sits in your application and collects performance metrics, and it sends it to the server, which is in yellow. The server is what the agent reports to. Its job is to process and persist the data collected by the agent and to generate the graphs in the UI we just saw in the previous slide. Today I'm going to be focusing on the agent side of things. So before we dig into the details, we should understand exactly what kind of performance data we need to be collecting. With the web application, our primary performance concern is the request response cycle. We don't want our pages to load slowly, we don't want slow AJAX calls, and we don't want our API to be slow. We'll consider the request response cycle to be our basic unit of measurement, and I'll call those transactions. There are other kinds of transactions too, like background jobs and any atomic process that we're interested in measuring. We could build our agent that just measures a transaction, but it would be nice to know the kinds of things that affect the duration of a transaction. It'd be nice to know things like database queries and view templates and how they affect our performance. So we want to measure those things as well. Here I'll refer to them as events. So we have transactions, the request response cycle, and we have events that happen within the transaction. We'll need to figure out how to instrument these processes. Here's the target for what we want. This is kind of a zoomed in of that screenshot. We've got a graph showing data for each of our application's endpoints, as well as a waterfall diagram that follows the execution flow for any one of those endpoints. So let's get an overview of how we're going to be implementing the agent, a general plan. In its current form, Tracebin is a Ruby gem that you can add onto any Rack-powered web application. Right now it has full support for Rails and Sinatra. Here's an overview of the workflow. It instruments the various components of the application, collecting some performance data. Then it stores it in a way that keeps the workflow thread safe. And then it periodically transmits the data that it collects to the server. So these are the three kind of topics that we'll be talking about. So now that we have a strategy and some terminology, let's take another look at the schematic to get a better sense of the life cycle of the data. So first, a request comes in, kind of at the top left. So when that happens, we need to initialize some temporary storage to collect the data from the events that happen. And so we instrument the application so that as the events happen, the events get stored into the temporary storage. And then when the request ends and the response is generated, kind of in the top right of the application box, we will add all of that data to a shared storage. As the data set grows, we'll periodically dump it all and send it to the server. So let's start with the first part, how to collect performance data. So here's where we are in the schematic, that red box. So measuring performance in our case is going to be all about measuring the time it takes for a bit of code to run from start to finish. So to do this, we'll employ what I call the benchmark pattern, and it's pretty straightforward. So let's instrument this method call on line 15. Remember, we want to figure out how long it takes to execute. So to do that, we just need to put a new time object before and after it executes. In Ruby, we get the current time with time.now. So we'll store those values so that we can calculate the duration of the method call by subtracting the two values on that takes place on line 18. The output of subtracting two time values is represented in seconds, but the decimal precision is preserved. And then we're done. So now the naive way to build a library around this concept is to stick it in a method like so. So we replace that method call to with a yield on line 17. Then on line 21, in this case, we can handle the events, and we'll talk about handling the events later on. So this would let the developer declaratively wrap different parts of their application with our instrumentation by passing a block to that method like so. So the method call that we're trying to instrument gets added to the block. So now there is one huge problem with this. It requires the developer to kind of litter their app with code blocks like this. Each time they want to instrument something, they will have to call this method. We'll need to find a way to eliminate this development overhead so that our agent can operate without the developer's intervention. So to do that, we will need to instrument the relevant components of the application. We'll need to break into the components code and observe their innards as they operate. This will allow us to work in the background, allowing the developer to kind of set it and forget it. Here are some different ways in which we figured out how this can happen, at least in Ruby. We have notification libraries, middleware, and patches. And we'll start with notification libraries. These are kind of built into a framework typically. For example, Rails gives us active support notifications. This will allow us to subscribe to certain events associated with most of the big parts of the core Rails components, like active record, action controller, and they trigger callbacks whenever those parts are executed. So this is how we subscribe to a notification. We just give it a string to identify the kind of event that we want to listen for and pass it a block, which will serve as our callback. So in this case, whenever active record executes a SQL query, the block that we pass in will get executed. So we can make our agent handle the event in this case, and we'll talk about how these events get handled later on. Here's an example of the payload that we get from an active support notifications trigger, that args variable that gets passed into the block. So we get the start and end times, along with some useful information, in this case about the SQL query that was executed. So this is useful, and we use it for the majority of our Rails instrumentation, but it isn't perfect. And here are some of the things that we sacrifice when we're using a notification library. First off, there might be some components that don't get covered by the library by default. Active support notifications, for example, doesn't have a notification for layout rendering, which would be kind of a useful thing to know about when it comes to how a transaction operates, since the layout kind of wrapped around all the other view rendering, the template and all the partials. So we could patch that part of action view to provide support for it with notifications, but that kind of leads us to our second problem. So if we rely too heavily on the notification library, we end up needing to require the library as a dependency, which we don't necessarily want to have happen, especially if we want to support other non-Rails libraries like Sinatra. So with that in mind, the best way to go about this use case is to use these libraries where they are already provided, but to also build instrumentation where they are unsupported. So for example, while Rails comes with notifications for active record, we'd also want to instrument database libraries at a lower level in case the app doesn't use active record. Our next option with instrumentation is to install middleware. Middleware is essentially a layer that we can put in between two application components so that we can, among other things, perform transformations on the messages that are sent between those components. In our case, we're just going to be measuring those messages. Obviously, rack is the primary library for which we can build our build middleware, but there are a few other libraries that adopt this paradigm, like Faraday and Sidekick. So here's a simplified example of the rack middleware that we use to instrument transactions. This isn't exactly the code that we use in the final implementation, but it's for illustrative purposes. So line 51 is where the application layer gets executed, where the rest of the middleware runs and Rails does its thing. So we want to wrap this with our timestamps. So for transactions, we use an abstraction called a timer, which does some other things to help us manage transaction data. So we'll start the timer and stop it after Rails does its thing. Then we collect the results. You might recognize this kind of code from pretty much any rack middleware tutorial that you find on the internet. This is essentially the same thing. So what happens when the component that we're trying to instrument doesn't have those nice built-in ways of measuring its execution time? One way to address this in Ruby is to do a little bit of metaprogramming. Our basic way to do this is to dig. Our basic strategy for this is to dig into the library to find the method that we want to instrument. So for example, if we want to measure database queries, the relevant method in the Postgres adapter for Ruby is the exec method on the connection object. We then wrap that method call with benchmark pattern, and we handle the information that we acquired. So here's a code example. We use class eval to crack open the connection class, but there are other ways to do this in Ruby. So first we add an alias to the method so that we can reference the old version. That's on line 32. Then we then re-implement the method and capture the original method call. So the re-implementation starts on line 34, and then the old method gets executed on line 36. We pass along any arguments since we don't really need to do anything with them. We add a start timestamp, a stop timestamp, then we process the result. So like I said, there are a few other ways to do this in Ruby, but they essentially achieve the same result. In other languages, there are different ways of doing this. So for example, in JavaScript or any other language in which an object's methods are like first-class values, we might want to just overwrite the relevant function after assigning the old one to a different variable. This is just Ruby's way of doing that, since methods can't be passed around. So what do we sacrifice? First off, at this level, since we aren't dealing with abstractions, we'll need to make patches for multiple different libraries that do the same thing. For example, if we want to instrument database queries, we'll need to patch multiple adapter libraries like PG, MySQL2, Mongoloid, and so on. If the developer is using an adapter for which we don't provide a patch, their SQL queries won't be instrumented. Second, there's also a pretty major maintenance issue that we marry ourselves to when we decide to patch a library. We need to not only follow the changes in the library's API, but also maintain compatibility with older versions of that library and find ways of detecting those versions. This will result in a lot of logic that deals with version and compatibility checks. So regardless of the instrumentation method that we use, building our agent around these patterns will allow us to build an agent that is completely transparent, so that the developer doesn't have to touch our library for it to work. So now that we have a way of acquiring the data, what should we actually do with it? So in order to address this, we'll need to keep a few basic considerations in mind. We want to minimize both our memory footprint as well as the runtime effect on the parent application. In other words, we don't want to put our finger on the scale. Since we're trying to measure performance, we also don't want to do anything that negatively impacts the performance. we also want to maintain this idea of transparency that I discussed earlier. We don't want any developer intervention. To get the idea of the general strategy that we're going to use, here's the schematic diagram again. I've highlighted where we're at. So the request comes in, we collect the data, and now we need to find ways of storing the data and passing it on to this shared storage to be passed to the server. So with that in mind, we'll need two different components for this. So first we need a place to temporarily store our event and transaction data as it is collected. And second, it would be nice to have a central place for this data to be put so we can upload it easily. So we have those two little hard drive icons that we're going to be focusing on. So the easiest way to do this is to just have a couple of objects like an array or a hash or any kind of data structure. We'll collect the transaction's event data into one of those data structures and then add it to the shared one when the transaction is finished. Now there's one big problem with this. We'll have to account for web servers like Puma and Unicorn that are built to handle many concurrent requests. They operate by handling separate requests in multiple threads. So here's an example of how that's gonna need to operate. We have the multiple requests being handled at once, each on their own individual thread, and with their own individual storage structure initialized. So we'll need to pull all that data from those threads to a shared location. Therefore, the two potential problems that we need to account for when developing a storage strategy are this idea of thread corruption and thread contamination. So we need to make sure that the states stored in these threads don't get corrupted. With Ruby and MRI in particular, though, we don't necessarily need to be concerned with memory level corruption, but there can potentially be this issue of data being written erroneously, thereby invalidating certain states. We also need to make sure that events taking place in one thread don't get accounted for in other threads. They don't contaminate other threads. Both of these kinds of things happen when resources are being shared across multiple threads. And that's exactly what's happening in our case. To address the second concern first, we and most other agents we've looked at use what's called a thread local variable. This is a variable that is only accessible to the current running thread. So in Ruby, this takes the form of a hash-like structure that can be accessed from the object that gets returned from thread.current. In this example, we assign a value to a thread local variable on line 14, and then when we try to create a new thread and access it from that thread, we get nil. That's because that value wasn't added to the thread.current in that new thread. So it's only accessible from if we can assume that this is running from main, right? So the thread that gets initialized on main has that value, but no other threads have it. So our agent assigns an array to a thread local variable when the transaction starts. Events get shoveled into that array as they occur. This lets us collect events in separate transactions without erroneously accounting for events that occur in other concurrent transactions. So when it comes time to persist the transaction data in that shared storage, we'll need to consider the idea of thread safety. We'll need to store all of our transactions in one spot, which will make it prone to thread corruption. Since multiple transactions might be occurring in multiple threads at once, each thread is trying to access that resource. So the pure Ruby way to handle this is to use a mutex, which will lock threads out of a certain block of code while one thread is executing it, forcing them to wait for that thread to finish executing it. So here's where our first brush with our library's single dependency happens, so I should mention it here before going any further. Like we just saw, Ruby has some low-level ways of dealing with concurrent workflows, but like I said, they're pretty low-level. requiring a lot of boilerplate, which make these workflows error prone and less expressive. This is why we've decided to use concurrent Ruby in places in which we deal with multiple threads. It provides some better abstractions in these cases that are more aligned with the concurrent, the classic concurrency patterns. So concurrent Ruby gives us what are called thread-safe data structures, which are basically wrappers for arrays and hashes. They implement this locking logic for us, allowing us to treat them like they're pure Ruby alternatives. In a way, this makes our code look almost exactly how it would look if we weren't accounting for thread safety, since we can use these objects just as their pure Ruby alternatives. So now that all our transaction data is in one place, we need to send it off to the server. As it is with most other agents, we'll do this with an HTTP request on an endpoint to the server. So first, let's call the basic considerations that we laid out earlier. In essence, we want to be as invisible as possible to the host application. This is also true when we're working on transmitting the data. Let's look at the basic workflow for this. Every time we want to send the data to the server, we need to first unload the storage, unload all the transaction and event data from the storage. This needs to be a thread-safe operation, so we don't interfere with other threads trying to dump data into that storage. We then need to send the data to the server over HTTP, and we need to handle failure cases. But I won't go over those failure cases today. Again, this entire process needs to take place on its own thread so that it doesn't interfere with the application. So luckily, concurrent Ruby provides us some pretty good solutions for this. So let's explore our options. The naive way to do this is to transmit the data at the time that we collect it, that is, send it immediately after the transaction finishes. So the transaction finishes, we send that transaction's data with a single HTTP request. With this, our concurrent Ruby abstraction of choice is a promise or any of its cousins like async or future. This will allow us to create an asynchronous process in which the HTTP request can be made, thus letting the application finish processing the transaction as intended without having to wait for our server to respond, which would be a big problem. This would allow us to curtail a storage strategy altogether as well, since data is being sent as soon as it is collected. Now, the biggest issue, obviously, is that it requires an enormous amount of overhead, since HTTP requests require a lot of overhead to be initiated, and this requires a lot of overhead for both our host application and the server to which we're sending the data. So as a side note, this kind of raises an interesting consideration. We're dealing with large amounts of data that had to be written to a database on the server side somehow. So after we send the data to the server, it has to be written. This process takes a certain amount of time since we're being constrained by the laws of physics. This means that if we are transmitting a chunk of data at a rate that is higher than the rate at which the server is able to process it with all the HTTP overhead included, then it will never finish the task of processing all our agent's data. While this seems like it shouldn't be too much of an issue with sufficient computing power and fast storage, it did cause some problems in our early prototypes and thus informed how we decided to move forward. So our next option, and this is actually the option that the current version of our agent uses, is to set a time interval at which we set and send the data. So we need to send it every n seconds, maybe every 60 seconds. So for that, the concurrent Ruby has a timer task that we can use, which will just execute a block every on a given interval. This is an asynchronous process happening entirely outside the normal flow of a transaction, so it won't interfere with transactions. While this is our current strategy, we do anticipate the problem arising with applications that receive maybe hundreds or thousands of requests per second. If we don't transmit the data often enough, the data structure in which we store it will grow to a non-trivial size in that shared storage. And that violates our principle of minimizing our agent's memory footprint. If we transmit the data too often, we'll run into the problem that I discussed in the last slide, which is the task of persisting data, in which the task of persisting the data will be too much for our server to handle, and the data set will grow faster than we can store it. So there are a few ways of managing this, and we noticed other agents will write some of that shared storage to a file, or sample our transactions at different rates. But within the scope of this kind of section, we could also make our transmission mechanism a little smarter. What I mean by that, so instead of sending the data on a set interval of like 60 seconds or so, we could monitor the size of the data set, sending the data after it grows to a certain size. This is obviously a problem for applications at the opposite ends of the spectrum. So if an application seldom receives requests, it will hardly ever reach the point at which this size trigger would happen, because the data set won't grow fast enough. So the best solution would probably be a hybrid implementation of both of these strategies so that we get the best of both worlds. But at this time, we're just using the former. We're sending the data on a set interval. So that wraps up the key patterns that I've discovered throughout the process of developing the Tracebin agent. So in conclusion, here are some main things that we learned, hopefully in a general enough format that they can be applied beyond this project. So first, it doesn't take a whole lot of time to build instrumentation for most web application performance. In fact, the vast majority of the code that we wrote deals with compatibility in edge cases. The core workflows of the agent are super slim. So to keep the agent slim, we want to make sure that we understand where most of the computation occurs. Anything that takes more than constant time or requires waiting on another process, like a web resource, that should be offloaded to an asynchronous task. When we move complex tasks to other places, this not only helps keep our finger off the scale, but it also allows us to optimize performance where it counts. And this theme also translates to our serverless implementation. Finally, while there exist a lot of libraries that could have helped us accomplish some of our goals more easily, we took the disciplined approach of writing our own code. This kept our agent lean, and it also helped us solve a lot of different problems in a lot of different problem spaces that we had never encountered before. So it was a wonderful learning experience. So that's Tracebin. As promised, here's my info. I'm seeking opportunities now, so if you have any questions, feel free to get in touch. Thank you very much.